Hello, my Algebra 2 students. It's day 7, and we are starting with a little exploration here in our calculator. But we're going to get talking about natural growth and decay. So you may have heard that terminology before. So first thing, when it says, what is the value of the expression 1 plus 1 over n raised to the n power as n gets bigger and bigger and bigger, meaning as n heads off to infinity? So to figure this out, into my calculator, into my y1, I put the expression. So I put in 1 plus 1 over x and then raised to the x power. All right, to do this efficiently, I changed my table setting to ask. So walk through this with me. So the first one, if we put in 10 to the first power, so 10 to the first power is just 10. The value comes out 2.5937. So what that actually means is if I do 1 plus 1 over 10, raise it to the 10th power, that's what I'm going to get there. Next one, 10 squared. Well, that's the same as 100. So let's put in 100. The answer comes out 2.7048. So that gets a little bit bigger because this would be 1 plus 1 over 100 raised to the 100th power. All right, 10 cubed is 1,000. If I put 1,000 in, I get 2.7169. So it gets bigger, but not a lot bigger. And then as we keep increasing the value, let's put in 10,000. That value increases, but not much, 2.7181. All right, let's put in 100,000. So 1, 2, 1, 2, 3. I was counting my zeros there, 2.7183. And then if we put in a million, 1, 2, 3, 4, 5, 6 zeros, we get 2.7183. So rather than the number getting bigger and bigger and bigger, it starts to level off or plateau off to a single value. So when it says, do the values in the table appear to be approaching a fixed decimal number? Well, yeah. If so, what number is it rounded to 3 places? Well, these last few match to 3 decimal places, and that's 2.718. So the conclusion, this part here, is what we can say is as the n value got bigger and bigger and bigger, the value of 1 plus 1 over n raised to the nth power, that starts getting closer to this value 2.718, which what that value is known as is e. So it actually has its own little variable to go with it. Oh, a little lowercase e. And so if you'll see the definition e, they're saying it's a mathematical constant, sort of like pi, that is used to model growth and decay that is changing naturally, or you can say continuously here. So it's sometimes referred to as, here's where you can put natural growth or decay. So E is about 2.718. The same way we say pi is about 3.14, E is about 2.718 here. Now, that means there is an E button on the calculator. It gets its own special little button here, which we will talk about in just a second. So the parent function, if we look at like, well, what does this look like to graph it? Well, you know what y equals 2 to the x or 3 to the x looks like. So having a base of e, it's going to look really, really similar. And so if we think about e to the first power, well, that would be e itself, or about 2.718. E to the negative first power, well, rather than making you type in 2.718, let me show you where that E button is. Let me see if I can get rid of that glare. All right, so down here, I'm going to slide my calculator up. Right here, you're going to see on and then store, and then above that, a button that says LN on it. Above that is a little E to the X. So if you hit second and then the LN button, you'll activate it. So second, LN, and then on your main screen, you're going to see E raised to something. So let's fill in the something. If I do E raised to -1, that's going to be 0.367. If I do E, so second, LN, to the 0, well, that's 1. We knew that was going to happen. What about E squared? So E squared, about 7.389. And then let's do one more. If we do E raised to the 10th power, oh, look how big that gets, 22,026 and change. What that means is because E is a value greater than 1, this is going to be an increasing function. What we see is that it crosses right here at 1, right, the y-axis, and then to the left, it's a little bit smaller, to the right, a little bit bigger, and then a lot bigger, and then it shoots on up, basically, towards infinity here. So the graph is going to look like that. That's what y equals E to the x looks like. So that models natural growth and decay, which all that means is that when you think about like the number of babies born in a year, they're not all born on January 1st. They're born throughout the year. They're continuously being born. So that's where that vocab kind of comes in, that it's not that they all happen on the first of the month. It's just that growth consistently keeps happening. All right, on to the next page. For these ones here, this is just showing that just like any graph, we can transform it. So it's more practice than it is anything else. So let's maybe just look at one of them. So as a reminder, anytime we're trying to transform function, I have to bring it back to a basic old parent function. So e to the x would be the parent, like what we just looked at. The y-intercept is right here at 0, 1. Horizontal asymptote would be y equals 0. An accuracy point. If I plug in x equals 1, then I would get out e. So 1 comma, remember what that is, 2.718. So 1 comma 2.718 would be my accuracy point. All right, what are the transformations happening here? Well, I wanted to look at this one because they're a little different. The 2 in front would be a stretch, but I want to start closer to the variable. That negative in front of the x, that's a reflection. Over the y-axis, we don't see that one all the time. The 2 in front, that's a vertical dilation. So let's think about what the original looks like. We just said the original is this little increasing function. We are now going to take this thing, flip it over the y-axis, and stretch it. So take the point 0, 1 right here. If we reflect it over the y-axis, that doesn't move. But if we dilate it by 2, the y value gets multiplied by 2. So it moves up to here. The horizontal asymptote right here. All right, flip it over the y-axis. It's still the same line. It would literally, throw my pen. It would go like that. All right, and then from there, if we dilate it and multiply it by 2, it still doesn't change any because 0 times 2 would still be y equals 0. All right, and then the accuracy point. Let's try. If we take the point 1 and then 2.718, so like let's say it's here-ish. Maybe I'll do that in pencil. So like about there. If we flip it over the y-axis, it will come back to here, and then we're going to double the y value. So 2.718, let's see, times 2. It's about 5.4-ish. And then as for my y value, it flips, so it's back here at -1. So -1 and then 5.4 approximately. So 4, 5. So like here. All right, so think about what should happen. You took that little baby graph, you flipped it over the y, and then stretched it out a bit. It's going to look kind of like that right there. All right. We'll save the other one to chat about in class. Let's keep moving. So why we talk about this natural growth and decay. It's saying interest that is continuously compounded, right, is modeled using an entirely different equation. And what the equation looks like, we lovingly refer to it as the PERT formula. It's P times E raised to the RT. And now think about where that comes from. It would normally be 1 plus, R, let's say to the over n, and then raised to the nt power. We just looked at what happened when 1 plus 1 over n raised to the n power. That turns into E. You can kind of see how this equation like morphs into this guy. E replaces the n's. The r gets bumped up into the exponent there. It's very easy to use, so let's try it. It's saying suppose that we have $1,000 invested at an annual rate of 8% compounded continuously. All right, that is our code word. to know that we're going to use the PERT formula here. So this p-value, that's 1,000. The r value, it still goes in as a percent, or excuse me, as a decimal, so change that to 0.08. And then the t value is they're saying after 10 years, so that's going to be this. All right, let's try it. We have 1,000 e raised to the 0.08 times 10. So calculator, on that home screen, 1,000 second ln, so there's that e, and then raised to the 0.08 times 10 up there. So that means that if it's compounded continuously, you would end up making a lot of money right here. That more than doubles your money in 10 years. And so it's the idea that at every moment of the day, they are calculating that new interest. It's the most you could possibly make, which is kind of nice. All right, last part. How long before the account grows to 3,000? Well, at 10 years, we're at 2,200 and a little more. So it's going to be beyond 10 years. So we know that right now. It's going to be something greater than 10 years. And so if we want the A value to be 3,000 for what T value, let's put the 3,000 in on the left, 1,000 e to the 0.08 t. Now from here, y1, y2, into your y equals 3,000, 1,000 e raised to the 0.08 x in this case. All right. If I hit zoom 6, you should know immediately we're not going to see anything. I'm just resetting it from wherever I last had it, because the y value at 3,000, not going to see that. So let's change the window. My y maximum, I'm going to change that up. I'm going to make it 4,000. I want to be able to clearly see this. And now hit graph. So there's my y1. And now I can tell they're going to intersect, but I can't see it. But I already said it's got to be bigger than 10 years. So I could have actually changed my window. It's just sheer habit that I don't change more than one thing at a time so that I don't get lost in the space of the graph here. All right, so I made my X max 20. So when I sketch this, I do want to kind of show that I'm out at 20 here. I'm up to 4,000 here. All right, here is my Y1. And coming in here, here is my Y2. We want to know when that's happening. Second, trace, intersect. Remember, that's showing your work by stating what you're doing there. So slide on over, enter, enter, enter. And it says how long before it grows. So it would be about 13.7, and that would be 13.7 years before it reaches $3,000. All right. Let's do one more together. This next one, it's saying in a state park, the deer population is estimated to be 2,000, and it's decreasing continuously at a rate of 4% per year. I almost hit a deer this morning, so I believe that the population could be decreasing. I did not, though. So if the deer population decreases as the same rate as above, what's the expected population to be in 10 years? All right, so a few things. The continuously is how I know we're going to use PERT. The details. Population, so that's the p-value, is 2,000. And then it's decreasing at a rate of 0.04 percent, or 4%, but we make that 0.04. All right, if we plug all of this in here, we end up with A equals 2,000, and then E raised to the 0.04 t. Now, the only thing you might be thinking of here is if we plug in a value right now of 10, it's not quite going to look the way that we want it to. And let me show you why. If we go 2,000 e to the 0.04 times 10, that gives me a bigger number. To show decrease in this case, we make it negative. So if I wanted to show a decreasing rate, make it negative. So now I'm just going to adjust that little equation I just typed in. So I'm going to insert a negative sign right there, and there we go. Now the population's going down. So if it's 1 plus or minus r, you make it a minus when it decreases. In this case, if it's decreasing, you make it negative. So at least those two should kind of make sense. So I end up with 1,340.64 and change. Since we're talking about population of deer, just round. So like 13, maybe 41 deer is what they would expect if that population decreases at the same rate for 10 years. All right, the second piece. In how many years will the deer population be half of the current population? Well, current population is 2,000, so half would be 1,000. And they want to know in how many years. So we are looking for T. All right, 1,000 goes in on the left, 2,000 E raised to the negative 0.04 T goes in on the right. So Y1, Y2. So we have 1,000 here, and then 2,000 E raised to the negative 0.04, and then X. I'm just going to hit graph because I actually think my last window might work out okay for this. Ooh, perfect. It just made it in there. So on my sketch, my window from last time was 20 and then up to 4,000, which is a little much for this guy, but that's okay. So when we put this in, here's Y1, Y2, and then finish it out. Second, trace, intersect, slide on over. And what I want to know as your video question is, what do you get here for the T value? Thanks for watching, guys. We'll finish the last one together in class tomorrow.